Good evening to everybody. So today we are going to discuss about covariance functions for random process as well as ergodicity and types of ergodicity. And the last two topics of this unit, that is Gaussian random process and Poisson random process. So while we are coming to the covariance functions, there are two types of covariance functions are there. The first one is autocovariance function and the second one is cross covariance function. So the autocovariance function is a measure of interdependence between two random variables of a random process x of t. So if the same concept for random variables can be extended to random processes, and now we are considering two random processes, x of t and x of t plus tau at two time intervals t and t plus tau. Then the autocovariance function is defined as, just wait, I will show you with a mathematical formula. See here. So this is the mathematical representation of two random processes, that is x of t and x of t plus tau. So here it is x of t and x of t plus tau. And this one is also represented like this, that is Rx x of t comma t plus tau minus E of x of t and E of x of t plus tau. So we know what do you mean by Rxx and what is E. There is no need to discuss about again and again here. So but here we have to consider three considerations for this autocovariance function. So here the first consideration is nothing but if x of t is at least wide sense stationary random process, then its autocovariance function is nothing but the subtraction of this one is the mean value, that is represented mathematically like this. So see here, this is nothing but the autocovariance function. And this is nothing but Rxx, which we had discussed in our earlier classes. You know that. And this is x squared bar. Right? So by this, we are going to know that here the autocovariance function is a not function of absolute time, that is t. And for the second consideration, here we are going to make tau equal to 0. Now we will see what happens if you replace the tau with a 0 value. See, if you place tau equal to 0, then the autocovariance function becomes the variance of the random process, right? And the third consideration here is the autocovariance coefficient of the random process x of t is given by the formula. Just wait, I will show. So say here, so this is the formula to calculate the autocovariance coefficient of the random process x of t, which is cxx of t comma t plus tau by root of cxx t comma t cxx t plus tau comma t plus tau. So if you put tau equal to 0 in this equation, then it will becomes look like that. Rho xx of 0, that is equal to cxx of 0 by cxx of 0, which is going to give us the value 1. And also we know that this determinant of this coefficient, that is autocovariance coefficient, is less than or equal to 1. Just wait, I will show you with mathematical formulas. So see here, so if you place tau equal to 0, then the equation look like this. The magnitude of this autocovariance coefficient is always less than or equal to 1. So this is about autocovariance function, and now we are moving to the cross covariance function. So now let us consider two random processes x of t and y of t have the random variables at x of t and y of t plus tau. Then the cross covariance function is represented by the equation. Okay, see here. So this is the representation of cross covariance function, that is the expected value of x of t minus e of x of t into y of t plus tau minus y of t plus tau. This is expected value. Or it can be represented like this also. That is the cross covariance function cxy of t comma t plus tau is equal to rxy of t comma t plus tau minus e of x of t into e of y of t plus tau. So as like in the autocovariance function, here also we have to consider three cases. That is, in the first case, if the random process are at least jointly wide sense stationary, then the cross covariance function Cxx of tau is equal to Rxy of tau minus x bar into y bar. Just wait, I will show you the mathematical formula. So see, this is the representation of cross covariance function. This we know from our previous class. So this is x bar, we know very well, mean of x and mean of y, right? If the two random processes are jointly wide and stationary, then it has to satisfy this condition, right? The conclusion from this equation is that the cross covariance function is not a function of absolute time, but it is going to depends on time differences. So for this time differences, we had considered for it our previous classes also. That is here also tau equal to t2 minus t1. That is nothing but it is a function of time differences, but not it is a function of absolute time. And the second consideration here we have to consider here, if the two random processes x of t and y of t are uncorrelated, then the cross covariance function Cxy of t comma t plus tau is equal to 0. Just wait, I will show you again with the formula. So see, so this is the mathematical representation. If two random processes x of t and y of t are uncorrelated. You see, Rxy of t comma t plus tau is equal to e of x of t into e of y of t plus tau. So this is the condition for statistical independence. Here, the independent random processes are uncorrelated, but the converse is that it is not true always. Okay. So now finally, we are going to find out the cross correlation coefficient of the random process x of t and y of t. Just wait, I would like to show you the formula. So see, this is nothing but the mathematical representation of the cross correlation coefficient of the random variable. Right? Now we are moving to ergodicity. So what is the basic definition of ergodicity? We have to know here. So a random process is ergodic if all its time averages of any sample function are equal to the corresponding ensemble averages. So here the ensemble averages are nothing but the expectations. Okay. For example, the ergodic processes can use ensemble statics to compute DC values as well as RMS values. So the analysis of ergodicity is extremely complex, and in most of physical applications, it is going to be assumed that all stationary processes are ergodic processes. Now, we would like to see the statement of ergodic theorem. So the ergodic theorem is going to state that a random process x of t, then all the time averages of sample function of x of t are equal to the corresponding statistical or ensemble averages of the random process x of t. So there is a mathematical representation is there. So see here. So this is the mathematical representation of ergodic theorem statement. That is small x bar equal to capital X bar and Rxx of tau is equal to Rxx of tau. So in the previous class, we had discussed about what is Rxx of tau and this one also, right? So now we are going to see what are different types of ergodic processes are there. So in this ergodic process, we have 4 types of ergodic processes are there. The first one is jointly ergodic processes, and the second one mean ergodic processes, and the third one autocorrelation ergodic processes, and the fourth one cross correlation ergodic processes. Now we will see what is a jointly ergodic process. Let us consider 2 random processes x of t and y of t with a sample function small x of t and y of t. Then the 2 random processes are said to be jointly ergodic if they are individually ergodic, and also the time cross correlation function is equal to the statistical or ensemble cross correlation function. Just wait, I will show you the formula. Okay, see. So this is the mathematical representation of jointly ergodic. So here the time cross correlation function is equal to the statistical or ensemble cross correlation function. So this is the one, Rxy of tau, which is equal to Rxy of tau. And here the small x bar is equal to capital X bar and small y bar equal to capital Y bar. And this is Rxx of tau is equal to Rxx of tau, comma Rxy of tau is equal to Rxy of tau. And if you are considering this for y also, we are going to represent like this. So this is about a jointly ergodic process. And now we are going to consider the second type, that is mean ergodic process. The random process x of t is said to be a mean ergodic in the mean if its time averages of any sample small x of t is equal to its statistical average x bar, which is going to be treated as a constant, and the probability of all other sample functions is equal to 1. So this is valid for all sample functions, that is small x of t. So just wait, I will show you the formula. So see, this is the mathematical formula, right? E of x of t is equal to x bar, that is a into x of t. So this is valid for all x of t, right? And now the third category, that is autocorrelation ergodic processes. A stationary random process x of t is said to be autocorrelation ergodic or ergodic in autocorrelation if and only if its time autocorrelation function of any sample function x of t is equal to its statistical autocorrelation function of x of t. And it is represented mathematically like this. So see, a into x of t into x of t plus tau is equal to expected value of x of t into x of t plus tau. Or in other words, this is also equal to r xx of tau, that is equal to r xx of tau. That is the time autocorrelation function is equal to its ensemble or statistical autocorrelation function, and it is represented by the equation, right? Now we are moving to the last category, that is the cross correlation ergodic process. Let us consider two stationary random processes x of t and y of t, and they are said to be cross correlation ergodic processes or ergodic in cross correlation if and only if its time cross correlation function of any sample functions, that is small x of t and y of t, is equal to its statistical cross correlation function of capital X of t and capital Y of t. So it is also represented mathematically. So see here, this is the mathematical representation of this cross correlation ergodic process. So this is nothing but a time cross correlation function, and this is statistical correlation function. So this is about ergodicity and types of ergodicity. And now we are moving to Gaussian random process, right? So Gaussian random process. Let us consider a continuous random process x of t, and now let n random variables are there. That is the first random variable x1 is equal to x of t1 and x2 is equal to x of t2 and so on up to we have n number of random variables are there. That is xn is equal to x of tn. And these random variables are defined at different time intervals. That is x of t1 is defined at t1 and x of t2 is defined at t2 and so on. X of tn is defined at the time interval tn respectively. And if these random variables are jointly Gaussian for any value of n, that is 1, 2 and so on up to n number of values are there we have at any time instance t1, t2 and so on up to tn. Then the random process x of t is a Gaussian random process. Now we would like to see the joint density function of this Gaussian random process. So see, So there is a Gaussian random process equation. Here we have x1, x2, and so on, xn, t1, t2, and so on, tn we have. So this is the mathematical representation of the Gaussian random process. That is the joint density function of Gaussian random process. We know what is Cxx and x minus x bar and Cxx here also. There is no need to discuss again and again, right? So here the x bar is equal to this one. The x bar is equal to expected value of xi, that is equal to x of t. And Cxx is nothing but cross covariance matrix, and its elements are nothing but Cik. Straight I will show you with the formula. So see here. So these are nothing but the elements of the cross covariance matrix, right? So here Cik is the autocovariance of x of ti. This is the one, x of ti, and x of tk. So see here, this is xi and this is xk. That is x of ti and x of tk, right? So if you expand this equation, what happens? Now we will see.